And I'm here to introduce your speaker, Steve Castellani. He's the owner of Puzzlebox Productions, LLC in San Francisco, and the technical director at iMagnet Limited, also in San Francisco. His activities include advising or consulting on serious, innovative projects in any areas of interest, particularly brain-computer interface, rapid prototyping, mobile applications, education, and disruptive technologies. He works with nonprofits using innovation, particularly technology, to improve society. His previous experiences include positions as a principal support consultant at Rocom Wireless and Bulletin Wireless, and a systems programmer at the University of Pennsylvania. And the reason why I'm introducing him here, last but not least, he is a graduate of Villanova University. I was very pleased to have him the first 3 years that I was working at Villanova in my artificial intelligence course and in my programming languages course. And I have a little story to tell you about it. I mean, I had a programming languages course. It was the first time I was teaching this. And I got this, we were teaching the students how to work with Perl, okay? Practical extraction report language. And students were wrestling with the syntax of it. And I get this submission from one of these students. The subject was Larry Wall, developer of Perl, is a crackhead. I thought, well, I'm a new professor. I guess this is what I have to look forward to from Villanova students. But I didn't realize how much I had to look forward to, because he had a little footnote next to it. I looked up the footnote. He had actually gone online and found that quote Larry Wall had attributed to himself. So this guy is a really accomplished researcher. Let me tell you, even back then, it was clear we were going to get the kind of performance we see today out of him. All right, so Steve, take it away.
Hey guys. Cool. So as Dr. Klassner said, and by the way, Dr. Klassner and Dr. Wei and Villanova Computer Science, thanks for having me back. It's good to be here. We're going to be talking about brain-computer interface. And can you guys hear me, by the way, in the back? A little bit-ish? Okay. Yeah, brain-computer interface. So we're talking about controlling computer software, robots, and machines with your mind, using thoughts, brainwaves, and all the rest. And the goal today is to kind of give you guys like a high-altitude overview of how it works, so you can actually have an understanding, and what's possible, what's not possible, and what's possible but not very practical. So by the end, hopefully you have a good understanding. And just to get out of the way, I'm giving you sort of like the Wikipedia summary here. So if you're actually interested in this stuff, it might be a little more complicated than I'm letting on, but the point is that you understand. So just appreciate that. And just to get started, Clint Eastwood.
Our weapon system is, as far as we can ascertain, one of the most advanced ever conceived. Couples radar and infrared detection devices with a thought-guided, thought-controlled arsenal on board the plane. The pilot's actual brain emissions are translated into a central computer through sensors in his helmet. Whatever target the pilot chooses is instantly destroyed without his even pressing a button. Or as quickly as his eye detects a threat, either visually or on one of his scopes, his thought impulses are guiding a missile to that threat. What this amounts to, gentlemen, is a 2 to 3 second speed advantage in reaction and attack time over any defensive system we have today. If the Soviets can mass produce it, it would change the structure of our world.
This computer's a little slow.
What about this thought control weapon system? No, you don't even need to press a button. Your thoughts are transmitted through the sensors of your helmet into a computer. The rest is automatic. Now, Firefox is equipped with missiles which drop from under the fuselage. There are 2 cannons from under the cockpit, and there's the real defense pod, which fires explosives backwards, which could knock out an attacking missile. But this is very important, Mr. Gann. You must think in Russian. You can't think in English, my man suppose. You must think in Russian. You think you can do that, Mr. Gann?
Yes.
right. Anyway,
This refitting.
okay, so can you shoot a missile from a jet fighter with your brain? Yes. And in fact, I'm going to show you some technology today that would in fact let you do that, and you can try it out for yourself. Would you want to? No. No, no. There's no point. The button's right there. Your whole body's evolved to push the button with your finger. If you want to push the button, you push the button. Also, you're not going to mistakenly think pink elephant and the missile fires off. And the thing in Russian is just total Hollywood, so just forget the Russian bit totally. So anyway, so what is actually going on here? Oh, by the way, Firefox, 1982, 30 years ago, 4 years before Top Gun, 5 years after Star Wars. You can kind of see a little bit going on in there. Yeah, we've come a long way, but Hollywood maybe not so much. Anyway, so what's actually happening? At the low level, and about as low as we're going to go, when your brain does stuff, electricity is produced. There's a whole lot of biology and chemistry and physics and so on going on as well. There's some chemical reactions that produce electricity and blah, 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 blah. Not important. All you need to know, when you do stuff, the area of your brain related to the thing that you're doing, there's a bunch of electrical changes. And we're looking for those changes in electricity. So when we talk about this, understand that it's changes in potential. It's measured in volts. So a single AA battery, 1.5 volts. The changes that we're looking for are in microvolts, so millionths of a volt. So 1.5 million times smaller than what's in a AA battery. And you can like hold a AA battery at both ends and you don't even feel anything. So very, very, very small fluctuations are going on here. And the equipment we're using is called EEG, anyway. This is an EEG. This is the lowest and most simple EEG out there. There is one electrode, and there's a little clip on your ear that acts as a ground and a reference. And all this thing does is it's a voltmeter. That's it. It measures at your ear and at your forehead, and 512 times per second, it takes a reading, and it sends it through to the computer. That's all that's going on. Everything that we do today is based off of that. So what you're getting, the only information, this little signal, 512 times per second, it's a voltmeter taking a reading, and then we use signal processing and all sorts of math and algorithms to get to extract what we're looking for out of that. So first, we're going to talk a bit about signal processing. And it's actually kind of simple, at least the parts that we're going to deal with. So here are some signals. We're going to deal with hertz, just like megahertz and gigahertz in a computer. It's cycles per second. So maybe you can see the mouse? Yes, sweet. Upper left, 1 hertz. So all the way across the bottom, 1 second, it's 1 hertz. So it goes all the way up, comes all the way back down, 1 hertz. This is 2 hertz. Pretty easy so far, 10 hertz, 20 hertz. So these are waves, and you can imagine, if your brain was operating at 1 hertz exactly, you'd get a wave just like this over 1 second. Now, of course, it doesn't actually look like that. It's a lot more complicated. So that's what's kind of going on here. This is a little more complicated of a wave. This is kind of what you might see, although it's a really, really clean and consistent signal. And I'm going to try to break it down for you a little bit. So this whole thing here is actually 4 different frequencies, you can say, 4 different waves in one. So there is a 2 hertz, a 6 hertz, a 15 hertz, and a 30. And so that you can kind of understand it, if you look at it, there's sort of this pattern that repeats going across. And if you look at it, this pattern it actually goes up, and it comes down, and it goes up, and it comes down, and it goes back up again. 2 hertz, right? So that's the 2 hertz component. This whole thing going up and down twice, that's 2 hertz. And then if you kind of look, there's like 2 ridges, and then a tall and a short. 2 ridges, a tall and a short, and so on. If you counted those, 1, 2, 3, 4, 5, 6. 6 hertz. Cool? And if you look at these two, 1, 2, so 1, 2, 3, 4, all the way across, you get 15 of those. And if you counted just the peaks, you'd get 30. So you can look at this wave, and you can actually understand that there are 4 signals going through, and there's some math that you can do to figure out exactly where those signals are. And that math is called a Fourier transform. It's named for a French guy who's also known for thinking up the greenhouse effect. Clever guy. 1862 he was born, so this stuff was all happening 200 years ago. I think the paper was published in 1811. Again, Wikipedia, so don't quote me on that. I don't really remember. Anyway, Fourier transform. All you got to know, because I took math here and I don't remember that much, but all you need to know is you throw some math at it and you get back some other stuff. And that is this thing down here. So you don't actually have to understand it, although you should, because if you want to do anything interesting, you actually do have to understand it. You throw some math at it and you get back these peaks. And if you look at it, this is at 2, that's at 6, 15, and 30. So if you understand so far that you're taking measurements 512 a second, and you can throw this transform at it, you can start getting measurements of what's in that signal, you're almost there. The way the brain works, there are a couple bands that we're interested in. Delta, theta, alpha, beta, gamma, and so forth. And the one we're really going to deal with today is beta, which is related to concentration and focus. So when you are concentrating and focused, if someone was measuring your brain waves, especially at the forefront of the brain, you would start to see measurements peaking around between 12 and 15 is low beta, between 15 and 19 or so is mid beta, and 19 plus is high beta. So if you take that signal off the headset and you run it through a Fourier transform, even if you don't even know what's going on through all the calculus and so forth, you can get some peaks out and you can figure out if someone's focused. Again, I'm making it a little bit simple, but hopefully you guys can follow that much. So once you have that information, you can start doing cool stuff with it. And before I get too far into some of the things that I've done at my company and that lots of people out there have done before me, I'll talk about some of the other things you can do. Each interaction with a computer, each type is called a paradigm. So this is one paradigm. You put on a simple headset with one electrode, you can get measures of attention. You can, by the way, also get, they call it meditation. It's alpha waves. It's sort of relaxation, not physical, but like a mental calmness. And the only thing you really need to understand is that alpha waves, I think it's between 5 and, I think it's between 8 and 12. Anyway, you can exist in both. So just like this signal has components in 2, 6, 15, and 30, you can be calm and you can be focused at the same time. They're not mutually exclusive. All right. So this is some software that we wrote. This is open source. You guys can download this. You can play with it at the end if you like. This is a program called Puzzlebox Synapse, or at least one of the functions of it. And this is just showing straight off one of these headsets your raw brain waves. And you can see here is 1 second, and here is just a close-up view of that same period. And you can notice there's this huge fluctuation here. That's an eye blink. So when your muscles move, you generate electricity as well. And you can see how much bigger that electrical change is versus the things we're trying to look for in the brain. And this whole section here, where this blink is happening, it's pretty hard to read that area. You can still pull a little bit of data out of it, but now it's a bit noisier. So the second thing you got to understand here is you need to sit still. If you're moving around, if you're jogging and running down the street, your muscles are twitching, you're generating all sorts of electrical noise, and it's going to be really hard to pull that signal out. Another thing is, remember, we're dealing with microvolts. The lights, they're operating at 60 hertz. They're throwing electricity around as well. These are such small measurements that the headset will pick up the lights. And it'll pick up, mobile phones are a very, very high frequency, but other noise that's ambient from electrical devices. All sorts of things are in the signal that you need to get out in order to get to your data. And the messier that it is, the harder it is. And one of the problems with these guys is with just that one point, that one measurement, it's really hard to eliminate other things that are going on, even across the scalp and other areas of the brain. So you're a little bit limited in what you can do with just the one electrode. And I'll show you some more of these later. This is consumer available. This is about $100 these days. This one, it's from $300 to $750, depending on which license you get. This has 14 electrodes and an individual ground and reference. This one has a combined ground and reference. We'll talk a little bit more about that. And then this is a high-end research grade EEG, which has electrodes. I don't know if you can see them, but there's little spikes in it. This is an active dry electrode. This is actually the cutting edge of technology. The earlier ones will require a cap like this, which isn't nearly as easy to put on or clean as this guy. And gel. You'd actually have to put gel in your hair, and you have to get it very finely aligned, and You have to wash your hair when you're done. It's very messy. This guy you can put on in about a minute, and you can start taking measurements. Obviously, this one you can put on in a minute as well, but you can only get that one point at the forefront. So jumping ahead, this is another screen of the same software. You can see down here a trend of attention over the last 30 seconds and that mental relaxation, those alpha waves over the last 30 seconds. And there's all sorts of spectral noise going out, and you can just ignore that for the moment. But this is a rolling 30-second average. Okay, another signal. So that's one paradigm. This is a totally different one. This is the P300, and this one's actually pretty cool. So the P300 is basically, imagine you lose your car, and it's in the parking lot somewhere, and you're walking up and down the roads of cars, and your brain is going, that's a car, that's a car, that's a car, that's a car. There's my car. Like that moment, that light bulb goes off, that moment you recognize that thing that you're looking for in a series of random events, there's a spike, there's this huge spike, 300 milliseconds later. It's a potential, it's 300 milliseconds, it's called the P300. They discovered this in 1964. So EEG's been around 100 years, actually. A lot of the research happened in the 60s, and it's been growing ever since, but the technology itself, like I said, it's pretty simple. So the P300, great, you can figure out when someone has saw something that they were looking for. What can you do with that? So the first interesting thing people did in the 80s was a speller. And that's this guy up here. They show a grid of characters on the screen. And if you are sitting there, sitting still, and you're looking at the grid of characters, they're going to light up very, very fast and randomly all over the screen. And say you want to spell the word dog, you stare at the letter D, and every few times a second, every once in a while, when that D lights up, your brain goes off 300 milliseconds later. It goes, the D lit up. That's what I was looking for. And the computer can recognize this. It takes maybe 7 to 20 if it's a bad signal trial, so a period of maybe 10 seconds. So not very fast, but something. It recognizes letter D. D goes up on the screen. You start looking at the letter O. And they use this for people who have ALS, Lou Gehrig's disease, cerebral palsy, who are physically paralyzed, who can't communicate, they can't move their body to write emails, to talk and communicate with the world.
Shows the Wadsworth BCI being used to write an email. The 8x9 matrix of letters, numbers, and function calls shown on the right is equivalent to a full keyboard. Groups of these items flash rapidly while the user pays attention to the item that he or she wants to select. The BCI analyzes the brain activity recorded from the scalp to determine which item the user desires. The result appears in the email window on the upper left. On the lower left is a predictive speller window that offers likely choices and thereby helps the user to go faster. With this matrix, the BCI user can operate any Windows-based program that can be used with a keyboard. In this email, the user writes simply, "Hello world."
This is the first email we received from our first BCI home user. He's using the BCI to answer questions from a reporter. All his emails finish with the sentence shown at the bottom. This video illustrates.
Cool. Make sense? So with the P300, you can do a speller. You can also have any sort of menu on a screen. So this is a useful way to interact. It's not terribly fast, but you can have a whole list of things you want to happen and control that with your brain. So we're going to talk about a few others, but just as a side note, one of the main researchers who produced the P300 back in '88 spun off a company recently called Brain Fingerprinting. And they're actually fairly controversial in the BCI community. What they do is they use the P300 as a lie detector for law enforcement. And the way they use it is they take a suspect and they sit them down and they present them with a series of images. And the images will be some things they recognize, some things they won't recognize, and some scenes from the crime or other individuals who are associated. And the person has to look at each image and press a button. Yes or no, I recognize this. So the EEG, the P300, it's not the lie detector itself, it's the pressing of the button. So if the person sees their house and they hit yes, you can correlate that with the signal. You'll see that, yes, the brain recognized that P300 signal, and they hit the yes button, that was telling the truth. If they see a suspect and they're guilty and involved, and they recognize the person, but they hit no, Their brain says yes, but they said no, and they're lying. Now, there's several problems with this. First of all, the brain is crinkled. So let me try to explain. If you took the brain and you laid it out flat, everyone's brain would pretty much do the same things in the same place. One might be a little bit bigger than the next, but otherwise, everything would pretty much be in the same place. But in order to fit in the skull, the brain wrinkles, and it folds in different ways. So imagine a baseball stadium, and you're standing outside, and you can't see what's going on the field, but every once in a while, the crowd just starts to cheer. And you can guess that by the cheering, you know something good just happened. Maybe the home team scored a run. Cool. But you don't know any more than that. Now imagine that you are in a hot air balloon above the stadium, and it's domed. You can't see anything. You can't see the field or the audience. And imagine they're doing the wave. They're going through all the way around the stands, up and down, and you can hear that cheer, and it's sort of moving around. Well, that dome, your skull, it's in the way. You can't quite tell, you can't quite pinpoint exactly where the wave is at any given point. You might say, oh, I think it's towards left field, I think it's towards right field. And you have the same problem with these electrical signals. They might be at a certain point, but the electrical noise hits the skull and it spreads out. So now it's over a wide area. But then remember, the brain is folded. So imagine that whole stadium and all the bleachers, and in order to fit inside the dome, they have to actually fold it and bend it, and people are sitting and facing every which way. Well, now that cheer's going this way, and it's going that way, and it's going back, everyone is producing these signals and broadcasting them in slightly different directions. And for some people, it might be back into the brain. For some people, it might be out to this region. Some people, a little bit over there. So the problem is with the P300 is that not everyone exhibits it, and not everyone exhibits it in the same region. This highlighted space down here is the typical area that you see it. For me, when I did this the first time, mine's all the way back here. So the problem with the P300, besides that it's not necessarily going to work, is that it's not agreed upon in the scientific community that it's sufficient to prove a falsehood or not. And yet, for the last 5 or 6 years, it's already been used in trials. It's already gone to a murder trial where a person was trying to get paroled based off of passing a P300 lie detector. And the judge in the case said, well, we accept the results of the lie detector, but we're going to deny bail for these other reasons as well. And what that did is it established a precedence, which said basically, well, we agree legally that this P300 is valid, but we're not going to use it in our particular case. And it's sort of a way, conveniently, for the judge to say, yes, this is legit, but I'm not the guy who's going to use it first. So that's the P300. The next one is actually the first one that I saw that got me involved. I thought this was really cool. I saw this on Slashdot in 2005. And the guy who was talking in the last video, and the guy who's going to be talking in this video, his name's Dr. Jonathan Wolpaw. He's up at the Wadsworth Institute in New York, in Albany. And he's one of the sort of largely recognized figures in this space. And I saw, I think it was a BBC article in Slashdot, and I said, this is cool, I want to see how this works.
It's the next generation of the Wadsworth BCI system, which we are currently working on in the laboratory. It will allow people to use brain signals recorded from the scalp to control movements in 2 and 3 dimensions. In this video, a person with a spinal cord injury is using brain signals to move a cursor from the center of the screen to targets that appear at various locations around the periphery of the screen.
And that's all in real time. And this is a longer one, but this also explains the same principle and how else it might be used.
This application relies on a 3-class BCI using EEG characteristics of imagining movement of the feet, of the right hand, and the left hand. Remaining completely motionless, a well-trained user can move to the right by imagining a right-hand movement, to the left by imagining a left-hand movement, and move forward by imagining foot movement.
Yeah, I apologize for the video. It runs fine on the single screen, but the dual, it's not working so hot.
This virtual museum visit application shows that the user can move around using 3 basic commands, although this can prove to be slow and tedious for long distances. application demonstrates another problem. This type of navigation using 3 basic commands rapidly exhausts the user because of the intense concentration required to move around.
See if that's any better.
We have created a new approach to navigation by thought, which allows the user to speed up his movements by using navigation points derived automatically from the scene to be crossed. With this system, the user must select the blue or yellow points that he wants to reach, while imagining left blue and right yellow hand movements.
All right, I'll just pause it and try to explain. Basically, the way that this is the Sensorimotor Paradigm, by the way. And what it uses, if you saw at the beginning, there's measurements right at the top of your head, right in the middle is the CZ area. There's just it's called the 1020 coordinate system. It just tells on every person where this electrode gets placed. When you move your feet, right at the top of the middle, there's a bunch of neurons that are related to your feet and they fire. And when you move your left hand just over to the right, there's a bunch of neurons that fire there. When you move your right hand, there's just a bunch that fire there off to the left. And the clever thing about this is when you think about moving your feet, when you think about moving your hand, the same neurons fire. So again, for someone who's paralyzed, if you can't actually move your hands or feet, you can imagine it and you can control a computer program or software. And as they explained in the video, that's all well and good. You can see the people hitting the targets pretty quickly, but it is tiring, it is a bit frustrating. It's like trying to flex a muscle that you've never used before. And it's great, but it's not enough on its own. So this system here, what they use, this is another open source program just like the last one. They have markers, virtual markers that you can select using your right or left hand. So in this video, the person's selecting the yellow marker with their right hand, and then they use their feet to say, I want to move there. And they can use their feet again to stop. And instead of trying to steer with this very difficult to navigate device, you can just highlight things and go. And if you think about it, there's no reason why you couldn't have those poles flashing and use P300 as well. And P300, remember, it takes 5 to 10 seconds, but maybe that's an easier way to say, instead of navigating down the hallway, say, go to the kitchen, or go down the hall, or just something selected from a menu. So when you take the Sensorimotor and you combine it with the P300, you now have a mouse cursor that you can click, and you have a way to select things from a menu.
Once a point has been selected, negotiating the way to the selected point is all.
And then the last paradigm that I'm going to show you guys today there we go, SSVEP. All right, so steady state visually evoked potential. What it means is, at the back of your brain, at the visual cortex, if you have a pattern on a screen like a grid that flashes, say 15 times a second, 15 hertz, your neurons at the back of your head, in order to recognize that flashing pattern, will start to flicker as well. The electricity will flicker at 15 hertz. So in this video over here, what you'll see is someone wearing a headset kind of like this. They're measuring the visual cortex. And if you look close, you'll see those patterns are flickering at different speeds. And one of the patterns is forward, another one's right, another one's left, and another one's reverse. And just by looking at one of these patterns, the brain synchronizes, and you can figure out which pattern the person's looking at. Now this requires no training, and it happens within 2 seconds. So if you switch from one pattern to the next, within 2 seconds, the system can recognize it. The P300 is specific to the person, and the Sensorimotor is also specific to the person, but more importantly, it requires training. The person who was steering that mouse cursor before, it took him 6 weeks to get to that point. So you can pick this up and measure attention immediately. You can do SSVEP immediately. P300 almost immediately, but it requires a little bit of per-person configuration. Sensorimotor configuration plus a lot of practice. So this robot is being steered by the person you previously saw looking at the screen, and you could see the live feed that was on that screen coming off the camera. So this is actually maneuvering relatively quickly. It's using your brain waves. For me, I think the motor rhythm and the P300 is much more interesting and much better application of the science. Cool, so what can you do with this stuff? Well, my company, Puzzlebox, like I said, a lot of what we produce is open source, and at least half of what we do is education focused. So the way we got established in this field, because I don't have a neuroscience degree or let alone a PhD, so I have no credibility. So instead I went out and started to do it. I looked at the technology and I saw what was possible. And based off the measure of attention, I started thinking about how some of the schools, I used to work at the Rosemont School in my part-time while I was a student here, they have these Lego kits, Lego Mindstorms, and in fact, Dr. Klassner introduced us to them. So this guy is a little bit more advanced than the one we use, but you guys probably have, do you have these kits? Yeah, sweet. So run off Bluetooth, and you can give them the motors, forward commands, left, right, and so on. So what I ended up doing was visiting some of the schools after building this robot and writing the software. And here's some kids using it. I think they're in Britain because they downloaded it. Go out to the schools and have the kids build robots in a team. So maybe one person's a little more design-oriented and they want to build and design the robot. Maybe another one is really good at that focus, either because they're good at it or because their brain happens to be oriented just the right way. Another person drives it, and so forth. You can break the kids up into teams, and you can have them race each other by focusing attention. So the goal of the exercise is to give physical, visual feedback and reinforcement by helping kids learn how to focus and pay attention. So I mean, I don't know about you guys, but when I was here, I had to write a paper. The first thing I did was clean my room, like do the laundry, check my email, everything I could possibly do, maybe like 3 or 4 in the morning. I'm like, oh God, I got to do this. And I'd sit down, and it would take a little while, but eventually the words would start to flow. I mean, part of it, you're getting things arranged in your head first, but part of it is that to actually sit down and focus, it's difficult, or it can be difficult. And the way we look at it is that here is an activity which allows you to practice that, to see that you are doing it correctly without having to write papers and all the rest. So that's one of the applications. After the robots, here's the software, actually. Pretty simple stuff. It's all written in Python and Qt. If you guys want at it, go crazy. It's not too difficult, I hope. Again, some of the visualizations. Next thing we did was radio-controlled helicopters. So here is how that looks.
Well, toy robots are a good diversion for some kids, but for the students in one Montgomery County classroom, robots are having the opposite effect. In today's, the teacher says, we're finding out why some robots actually help kids focus on their work.
It's not a battery that's causing this helicopter to move. It's not a remote control either. What's causing this helicopter or this robot to move is the power of these students' minds. Literally.
Yeah, it's like cool just to see how your mind can control them through a headset.
This is no futuristic fantasy. It's real, and it's the buzz among the 6th graders at the Rosemont School of the Holy Child. This robot is the brainchild of Stephen Castellati. He created software that causes the robots to move when these students are focusing intently on something.
What we're trying to do is teach the kids.
All right, so. Along with the actual exercise of modifying the helicopters, which, by the way, was something a client came to me and said, hey, I want to fly some helicopters. I had to learn how to do this, and I didn't actually have much of an electrical background. So what I ended up doing was I asked around. I'm based in San Francisco lately. Previous to that, New Zealand. Puzzlebox was formed in New Zealand in 2004. We've been going, I guess, 7 years now. Now based out of San Francisco. There's still a bunch of contractors based in New Zealand because it helps with the exchange rate. In any case, in order to learn how to modify the helicopter, after someone asked me, can you do this? And I told them yes, and then had to figure it out. Recorded the entire process. Did a time-lapse video of unboxing through the entire hack. And along with that, documented step-by-step the tools that get used. So an oscilloscope and what that is and how that works, and a logic analyzer and what that is and how that works. So this is, I think, a screenshot from that video that was produced. Took apart the circuit board, had to learn how the different pieces function, and not to get too far into it, but basically you have the joystick yokes on the front, And they're connected to something called a potentiometer. And what happens is you have the batteries running past the joystick, and when you move it, you can think of it as a sluice gate. So you think of a pipe full of water, and there's a sluice that controls how much water goes through. So if you have the joystick in the middle, it's midway open, and the voltage is, say, 3 volts. And if you have it up, the sluice is open, you get 5 volts. And if it's down, you get maybe 1 volt. And you could take a voltage measurement at each of those points and figure out where the joystick is, and turn that into a number and so on. For this particular hack, you can kind of see this little chip at the front, which was extremely convenient. That's the transmitter. So what happens here is there is a microprocessor on this remote control, and these pathways lead to it from the potentiometers. The microprocessor takes that measurement, and it converts it into a string of characters that send it over a serial signal to the transmitter chip. So what I did was took an oscilloscope to figure this out, and I had someone help me, obviously, and plugged this into a logic analyzer. And you can't quite see in this image so much, but you can see these little peaks and valleys. And what they actually are is hexadecimal values, so letters, literal A's, B's, all the way through, 16 characters. Each of these is a byte. So what you end up with is a string of 14 bytes, and each of the 2 sets can correspond to different joystick positions. So the way the flying of the helicopters work is took this microchip off, just desoldered it, plugged the power source into it, hooked a serial converter. I think I got one of these floating around somewhere. USB to serial adapter, just hooked up the correct pin to it, and read the string that comes off. So in the middle, you get a bunch of numbers and characters and letters and stuff, and you read it. And you store that string somewhere, and that's neutral. That's the helicopter sitting on the ground. Then you push it up to fly the helicopter, and you record it again. And you see that only 2 of the values have changed. So now you know which ones are up and down. And you measure you measure that threshold just as the thing takes off, and that's your hover. So all the software does is allows you to hover, fly forward, or land. So if you hit hover, it sends the string that corresponds to the one joystick being up just a little bit, the lift. And if you do forward, it sends both of the 2 joysticks forward, and then land just puts them back in neutral. So these measurements of concentration and relaxation, there's a trigger point where if your concentration is high enough, it sends the command to hover, and if it drops back down below, it sends the command to land. That's it. It's not terribly complicated. Hopefully it makes a bit of sense. And that video, we published the entire thing on Instructables.com. Got picked up by Wired, so we got a little bit of press on that, which was kind of cool, and just a great learning exercise. Later on, we did a wheelchair, electric wheelchair, on a similar principle. Again, this was a single direction, but we did a video, got an award for that, which was kind of nice. This was an art installation that we did over the summer for a huge art collective that does pyrotechnics. And what this thing is, it's about 30 feet by 50 feet. And each of these arches has 14 individual flame fireball effects. They call them poofers. It collects gas, and when you hit a switch, electrical switch, it releases the gas into this lit little like pilot light, and this huge fireball comes out. So for this version of the software, as you concentrate, the more fireballs start to go off. And we set it up so it can go all the way across the arc, or it can start in the middle and spread out. It's all individually articulated. We can control it any way you want. But yeah, so you sit there in a chair and you have this giant, enormous thing larger than this room. There's fire going off everywhere because you're focused. It's kind of fun. And there's a close-up of what that looks like. And then again, someone else had us do a radio-controlled car. That was a very similar effect. This one I did do the potentiometer instead of the transmitter chip. Took a multimeter, just measuring voltage, and just figured out at the different positions what voltage was which, and used an Arduino. Arduinos are really, really cool. I don't know if you guys have messed with them at all, but if you're into electronics or you're even curious about electronics, you can do amazing things without understanding much. And this we use an Arduino for. And then later on, I can actually show you guys this. These guys, this is an X10 Power Device. It lets you control electrical circuits from computer signals and a remote control, obviously, as well. This was done recently for a television show pitch, where the guy wanted to go into the executive office with a blender full of margarita, put the headset on the executive, and when the guy concentrated, it made margaritas. So it was a brain blender. And then, again, today you can play with this if you want. It'll control this lamp. Okay, so the next one was something we did back in March, which was kind of fun. This was an association with Neuro Sky, the company who makes the headset.
Over the past few days, a crack team of software developers from Neuro Sky and design engineers from Loughborough University have built and programmed an interface capable of controlling a 50-ton lifting crane using only the power of the human brain.
So just a minute, we're going to lift this car?
Yeah, with that crane using just the power of our minds. Wow.
These are celebrities in the UK, by the way. They don't necessarily look like it.
To succeed in this challenge, teamwork was key. So while Susie climbed aboard the cherry picker, the rest of us put on the ingenious Neuro Sky Mindwave headsets. These commercially available EEG biosensors pick up the mind's electrical impulses or brain waves, sending the data wirelessly to laptops that control the crane. It was all down to mind power. As I concentrated my mind, the coloured bar on the screen slowly increased in size.
It was a tense wait, but then Jason's concentration level rose high enough to turn the bar green.
I'm a superhero! This might be the coolest thing we've ever done on the Gadget show. The magnet's on, the car is engaged.
The car was airborne. It was a truly magical sight.
I'd done it! I'd finally hit the coveted green zone, and I wasn't going to let it slip. We've done it! Using the power of the concentrated mind, we controlled a 50-ton crane to pick up and transport a car, completing what could well be the most amazing Gadget Show challenge ever.
Deeply intimidating displays of mental agility and concentrations, you are Guinness World Record holders.
Right, so basically, here's how this thing worked. In case you were following, X10, Arduinos, potentiometers, USB to serial, logical analyzers, each one of these open source pieces fits into another larger project. So a lot of these little small tricks or games that are useful for education and practicing education actually has good business sense as well. Because then larger scale things, cranes and fireballs and everything else, people start going, oh, can you do this, can you do that? And that business case got proven. So here's how the system works for the Gadget Show. It was actually pretty simple. They have 5 hosts, so they wanted 4 to participate. So we set it up so that for the hosts, each one controlled 2 directions. So the crane would start at one end of the warehouse and it had to go forward and right, drop, turn the magnet on, lift it up, left, and then back. So we split it up across each of the hosts. Each one, we developed individual software interfaces for each of the people. They're large and bright, so they would show up on camera. That was the way they asked it to be done. The 4 computers just talk over Wi-Fi to my little laptop over here, which was running a control interface. Here's the 4 interfaces. And here's the control interface. This would actually be able to override or directly control the crane. You can see brainwave measurements and all this sort of steering, all that sort of thing. And this one laptop would receive from the other guys, and it would send it out through the Arduino to a little remote control device. You can see it if you're watching back in the video. There's actually, in the physical warehouse, they have a remote. That's how they normally move the crane. And the guys at Loughborough University, they built a little robotic device that goes around it and pushes the corresponding button. So all that I did at the Arduino is when you want to go forward, you turn on circuit number 0 or circuit number 1 or whatever happened to turn on the thing for forward, and the little thing would go forward, the little motor would turn, it would push the button. And when the concentration dropped, you tell the Arduino to shut off the circuit. So you're just turning a circuit on and off. And we got a Guinness World Record for that. So it's kind of fun. The project we're working on now, trying to do a commercial application. This is GDC, the Game Developers Conference. This is an international event, happens every year in San Francisco. It's not for gamers, it's for the people who create the games. And this is what we produced for GDC. I don't know if there's audio on this. But this is Call of Duty, Black Ops. That was the last release from last year. There's just been a new one. Here is a session of playing. That was the levels of focus and relaxation. You can see a rolling 30-second history in the upper right. and you can see instantaneous red and blue, red for concentration, blue for relaxation. And if you watch, you'll see as the person is hunting around, there's high levels of concentration. So you're focused, looking, where's someone going to be, you're concentrating. And if things calm down a bit, you can see the focus will start to drop. So walking through, going to reload, everything's calm, the attention starts to drop down. You come back out looking for people, attention goes back up again. So I'll let that play for a bit. Anyway, the purpose of this, and you guys can try this out too if you want to brought my Xbox. The purpose of this is for play testing. It's not for controlling the game, because remember, you only get one thing. You're not going to fire the gun with your brain. You're going to see what the person is experiencing as they play the game. So you imagine your typical Zelda game, you have a boss fight. Well, you want to make sure that the person is really focused and engaged in the fight. They're trying really hard, they're concentrating. You know that fight is well balanced. If they're playing and you can see from their score or from their progress that they're not really focused and they're just sort of whipping through, well, maybe it's not engaging enough. Maybe you need to make it more difficult. Maybe you need to tweak things a bit. Or if they're trying really, really hard and they're not making any progress and they keep dying, well, maybe it's too hard and you want to ratchet it back down. So the program that we're developing now, it's called Jigsaw. The initial release will be this month, actually. And it's not for the Xbox games, it's for social games. It has an embedded HTML5 browser. And it also supports Flash games. So especially out in San Francisco, there's tons and tons of indie shops, like 2 or 3 guys who they're just out of college and they want to make the next big Zynga Facebook game. So a lot of these small shops, they don't have resources for focus testing. They don't have people who can try out their game necessarily and give them feedback. So they can go to their friend, they can put on a headset, and they can use an eye tracker. And combining those with our software, you can see where they're looking. So you can see if they're dwelling a lot on one of the menus before they click on it, maybe your menu's not laid out well. Or if they're having certain difficulties in a certain area, or if you want to test things, we added some little JavaScript hooks that'll actually allow the game developer, when they want to test something, they can send a signal out that embedded browser or out through Flash back to our software to start the recording session. So if they're farming corn in Farmville and you want to make sure they actually care about it, not just bored, you can wait till they get to that point in your code, and then the moment they start farming, you can send a command to our software that says, hey, now I want to see what they're looking at, I want to see what the measurements are. And when it's all done, it gets fed back to the guy who operates the system. So that's pretty much it. Are there any questions? Anything else I can tell you guys?
So the electrodes are very sensitive, and like you're saying, like your computer monitor can use electrode interference.
Yep.
You just talked about this, but just like sweat can throw the electrodes off. So I'm really intrigued by how like your very, very simple like one electrode system
Mm-hmm.
can pick up on brain patterns and can consistently pick up on brain patterns and do what you want it to do.
It's touchy. It's touchy. The numbers that actually come off the headset, the algorithm, the Fourier transform, it's actually on the chip. And the numbers it provides you is a rolling 5-second average. So when you sit down, if you want to concentrate on the thing and make it go, it might take a little while for it to actually start to respond. It's not instantaneous. With some of the other ones, because you have more electrodes in more positions, you can start to filter out noise around the area that you're interested in, and it becomes much more instantaneous. So with the other guy, you can actually control it instantly and turn it off, just like a button. It's not as easy as pushing a button, so you're not going to use it in a jet fighter, but again, you can make it stop and start when you want to on demand. And once you start getting into electrode positioning in better places, then you can really steer the thing around. Again, as far as sweat, that wouldn't be a problem because that's just going to help with the conductance as long as it's not hitting other electrodes, but that's not really an issue. It's mainly getting the person to sit still and stay calm and relaxed. You're able to eliminate a lot of that noise. And there's a lot of signal processing that you can do to eliminate ambient noise. There's something called a notch filter. Without getting too far into it, you use it around 60 hertz in the States because all the lights and electricity operate 60 hertz. And in Europe, it's at 50 hertz. So these things have notch filters at 50 and 60 hertz. Throw away everything in that range. Don't even send it to me. That way, my signal's a little bit clearer. But basically, to answer your question, more electrodes and better positions is how you fix the problem. But for right now, it's a question of what can you do with what's out there. Is that about right? Cool. Anybody else? Yeah.
How long did it take you to open box the helicopter?
The first time, it was maybe a period of 3 weeks. There's something, I don't know if they're out here, I'm sure there's at least one in Philly, something called Hackerspace. If you've never heard of it, it's kind of cool. They're collectives. People join with other people who like do-it-yourself style activities like this helicopter modification. And they rent a space, and they form memberships, and they form committees to vote on how to use the space and to buy gear. I think the one that I went to is called Noise Bridge. It's one of the original hackerspaces. And I think it's like $80 a month for membership or something like that. But they have lathes and massive industrial sewing machines for people who do that stuff. All sorts of hardware for woodwork. They have massive benches of electronical equipment and extra like resistors, transistors, and all sorts of bits and pieces. People bring in old computers, old arcade consoles, like the full-size things. All sorts of gear people donate or bring in. They have brewing in the back, and they have like informal lessons. If you want to learn Python, you can show up and learn Python. There'd be classes that meet on that. So basically, I rocked up to them and just sort of said, hey guys, I want to do something with a helicopter. Anybody interested? Oh, by the way, it's going to be brain controlled. And a couple of people were like, hey, cool, let's see what we can do. In the course of a night, I found 2 guys who just happened to be there that night. The first time I walked in, and between the 2 of us, it took us about 5 hours to figure out how we were going to do it. It took about maybe 3 weeks of visiting 2 or 3 times a week to work it all out. And then the second helicopter took less than an hour. So the actual taking it apart, desoldering it, making sure all the wires were clean and all that sort of thing, and stopping to move the camera around. So the whole process took less than an hour, and I think it could be done within 15 minutes now. Anybody else? Yeah.
So I thought it was really cool how you were talking about you can pick up on different areas of the motor strip being activated, and so you can tell between looking at the hands.
Yes.
What's the resolution on that? Like, can you tell between like bending your wrist and bending your elbow?
Not so much. It's a bit difficult. There is one interesting principle to all this called neuroplasticity, which I should have mentioned. Basically, the more you do something, your brain physically rewires to get better at it. So the neurons move to get better at it. So what they were doing with this, in one example, is they had people, say, moving the cursor. And when they started off, they're picturing their right hand, they're picturing their left hand, they're picturing their feet, and they're using that to move the cursor around. Over time, they would ask the people who are getting good at it, well, what are you thinking about when you do this? And they kept on getting back the same response. Oh, well, at the beginning I'd think about my hands and feet, but now I just move it. So what they did next, because the brain had actually wired to get good at it, they said, well, that's cool. Try picturing your hands and your feet again. And they actually managed to get 2 different unique signals off the same point. So I don't have a video of it, but the more recent version of that software where the boxes are moving around are fully 3D. So now they have a 3D cube, and it starts in the middle, and they can hit any point at any corner of that cube by either doing the hand-feet visualization or steering the thing. And again, the brain will continue to rewire itself to get good again. So that's one way to do it. As far as different joints, they're too close together. It's too hard to tell, and from person to person, it varies so much, and there's a lot of noise, so that doesn't quite work. Anything else?
So going back to one of that answer.
Sure.
It looks like they have built new representations to control this novel tool use cursor moving. So it's almost like they had an extra hand or something.
Kind of like that. Kind of like that. Yeah. Basically, when it comes down to it, in the electrical signal, there's just a distinctive signal for what they're doing now versus the one that still moves their hands and their feet. They actually, there's a university down in Georgia doing something really, really cool with this. What they did was they worked with spinal cord injuries. So people who were born with no specific issues, but who had been, like say, in a car accident where the spinal cord had been severed or partially severed. And what they did was they had the person trained to move the cursor, and then they hooked the cursor up to a robotic arm. But instead of just moving an arm around, they made it a glove, and they put the person's arm in the glove. So they had the person doing the visualizations to move the cursor, except now it was moving the glove with their arm in it. And what they've been finding over time is it's very, 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 very subtle, but they're starting to get just a little bit of movement back in their limbs because the brain has found different pathways to produce the same effect. So that's neuroplasticity combined with all these different signals and stuff like that. So it's not something that on its own is going to solve problems for people who are paralyzed or spinal cord injuries. But maybe if you combined it with like gene therapies or something else, maybe there's hope. But either way, it's really interesting work that's going on with this stuff. And again, this is all non-invasive. This is all without getting into your head. If you want to look at the really cutting-edge research, there's something called ECOG. And that's taking the dome off the stadium. It's actually under the scalp. And they place electrodes directly on the surface of the brain. And they're doing really incredible stuff with that. That's where all the research is. One example is in the oral area where hearing is processed. If they place electrodes in that area, they can play music for you. And they can almost, not quite, but you can definitely get the beat pattern, reconstruct the music from the brain signals directly off the brain. So once you get rid of the scalp and the skull and all these things that are in the way, when you can actually put something on top of the brain, you can get some really, really in-depth controls. There's a famous video of a monkey years ago, at least 10 years ago, moving a robotic arm up and down and so forth. Reasonably well. They actually, it's kind of difficult to watch. The monkey it's sort of in this box, and it's been operated on and has these electrodes implanted in the brain, so actually damaging the brain as it goes in. And it's using a robotic arm to feed itself, and you're just watching it move it around, stuff like that. So that's something else they can do. They're not going to do that sort of thing with humans because it's so invasive, it's physically damaging. But by putting the electrodes there, you can start to do some really interesting stuff. One of the problems once you start to do that is there's a natural immune response where the area around that implant will start to like scar, so that over time it can become difficult for these devices to stay accurate. But if you wanted like a third arm kind of thing, you could do that pretty well, like moving your hand, by practicing that sort of thing, just by reusing neurons in a different area that they weren't used before. Some of these things that they're looking for the robotic arms, NASA is interested in it. One of the applications is for spacewalks. So right now, if an astronaut is working on a satellite or a space shuttle on the outside, they need to hold on, and they need the other hand to work with tools. And these suits are huge and bulky, and it's very difficult to work with these fine tools while you're holding on and you're trying to switch and so forth. So they're talking about using a robotic arm that's brain controlled that just does the clamping on, so that they can move that arm into position, and then they know that it's not going to move away, and they can use both hands to work on things, and they become much more productive, shorter spacewalks, and less risk and so forth. So there's other applications as you start to get into the higher stuff. Anything else?
The examples you showed were pretty impressive, but they were also kind of simple.
Yes.
How do you see this expanding to possibly become more complex or more quick or more sensitive?
Right. So that's one of the things we're working on, or at least that Puzzlebox is working on. Neuro Sky is pretty focused on these single electrodes. They're doing a couple different projects. The one they're just about to release are ears that are on a headband. So it uses your brain waves, and there's a video of a girl who's checking out a guy, and she's interested, her ears perk up. It's the same application, the same technology. It's kind of funny to see, and I think they're going to have it at CES and so forth. What I see is, if you have a headband, you got CZ, C3, and C4. You have that sensorimotor cortex. So one of the things that we've invested in the hardware for is to start getting those real, correct electrode placements and positioning them in areas that they're useful. So with these guys, you have to get past the hair and through gel and through whatever else and underneath hats and stuff like that. But what I see as next is just a headband with just the electrodes in position. At a recent conference that I saw, there's a new form of electrode which is kind of like these, except there's several concentric rings. And the way they do it is, I don't know if I have a good example, but back in the P300, if you were trying to get a signal from right there, you would put electrodes all around that area as well. Not to get the signal in the middle, but to be able to eliminate the noise from the outside. So with these new electrodes, which are a complete ring with an electrode in the middle, you can eliminate everything around one specific point and get very, very fine, accurate readings. So the main hurdles are better electrodes, ways of getting better placement, because if your headband shifts too far because you moved your hair, it's out of whack. It's some of those problems that people are looking at. And to be honest, it's still really, really early days for commercialization of all this. The only two companies that are really out there is Emotive and Neuro Sky. Emotive, they released that about 2 years ago. Neuro Sky, their customer headsets came out about 4 years ago, maybe 3-4 years ago. This is their original version. Single electrodes, these guys, there's these little pads that go inside, and you need a saline solution, contact lens solution. It's messy, and you can't wear it for very long. It starts to dry out. I think that once the aesthetic issues and the quality of the electrode and the placement solved, then you can start doing the more interesting stuff.
You mentioned for the P300 that the person has to be looking at a letter and waiting for it to flash.
Yes.
What was really the goal of that research there? Because the way I see it, wouldn't it be easier and faster to just measure where a person is looking at?
Like using an eye tracker? Yes, the reason they use this, again, a lot of this work goes for ALS patients and people with cerebral palsy and so forth. They might have motor control issues where they can't necessarily stay still at one specific thing. But even in their periphery, they can still see if the letter goes off. The other is, you have this tool set, and it's a matter of finding ways to use them. So the P300 is just pattern matching. So anything that is involving the brain's ability to match patterns is something that you can then apply, and the speller is one application of it. A little side point about the ALS patients and so forth. Again, Wolpaul, the guy who was talking before about the speller, they're up in Albany. They have a whole clinical program where they go out to outpatients, and they have nurses that go in and they use this technology. It's all interesting, but it's a good point you bring up because there's lots of limitations. First of all, someone who has ALS, usually lifespan's 4 to 6 years from diagnosis, and it's continually degenerative. So there's a span of the first couple years where you still have motor control to some degree, and you're going to use that first. So someone like Stephen Hawking, who has ALS, he still has access of his thumb, and he's also a very outside case. I think he's been diagnosed for more than 20 years, but he's managed to hang on. There's no reason you'd give him a P300 when he can still use his thumb to manipulate a joystick with speed. But there's this very narrow window in which if you are locked in and you can't move or communicate, it's pretty nice to have. You don't have to move your eye for it. You can just keep your eye in the center of the screen, but still be looking at the D, and it will still work. So the gaze tracking, sure, if you're able to move your gaze and hold it, that's going to be faster. But if you can't, this is your only option. Another one, actually, because people bring up wheelchairs and paralysis and all the other things. I've been to a couple of these conferences, and they take surveys of people who have these issues. And if you ask them, what would you like us to be able to? So when you go up to the green, there's a little light that you can kind of see in the back of your eye, and you sort of sit there and you get ready to take your swing, and you get concentrated and sort of loose. And when you see the light go off, you know that you're at that right state and you take your swing. They've used this for a U.S. archer and improved his rank within his division from, I think it was 18 to 6th by practicing before he would take his shot. There's breathing, there's getting in that zone for taking the shot with the arrow. But now you have this extra metric that tells you your brain is, you're actually focused, you're actually concentrating. So you get your breathing and the wind and all the positioning right, and you get this other symbol, and you take your shot, and he was able to enhance his ability past a certain point. Yeah.
It's clear that there's a lot of interest in this topic, and we're going to be having to stop the formal presentation now here. But I invite everybody, first of all, thank you very much.
Cheers.